Okay. So we will work out a few questions on Fourier series today. So we will apply the properties of Fourier series to solve some of the questions. Okay, so we'll start our discussion for today. So let us consider a periodic signal that is given by x yield of t is equal to 4 plus 2 cos 3t plus 3 sin 4t. So first of all, you need to find out the fundamental period. Then you have to evaluate the Fourier series coefficients. Then you are also asked to verify the Parseval's theorem. So to check whether you have actually gone through the properties of Fourier series, let me ask this question to Namita. Can you please unmute your mic and answer this? Have you gone through the properties of Fourier series that has been uploaded?
Sir, yes, I watched the video.
Okay. So I hope you are familiar with the word Parseval's theorem.
Yes.
Okay. What is Parseval's theorem state?
Total average power is equal to
Okay. So that I understand that you're going through that. The Parseval's power theorem states that you compute the total average power
of a
uh,
periodic
uh,
signal
of a periodic signal.
can be found by squaring and adding the absolute values of line spectrum.
Lines in the line spectrum. So
Lines in the line
that
spectrum.
Parseval's theorem, to compute the total average power, you have an integration in the time domain and you have an accumulation in the frequency domain. So I hope you understand that. So first of all, for this question, we will find out the fundamental period. So this is something that we had discussed previously in the initial classes. So you have a constant given by 4. You have a cosine wave of frequency 3 and you have a sine wave of frequency 4. So which means if you, this is in fact what is called as the trigonometric Fourier series expansion for x tilde of t. Because you already have a constant, you have cosine terms and you have sine terms. So you are given in fact a trigonometric Fourier series. And from this trigonometric Fourier series, you have to evaluate the fundamental period of the signal. And also the exponential Fourier series coefficients. Okay, so let us look at the fundamental periods. Let us look at the periods of the components that we have here. So the period of 4, no, that is a DC, so there is no period. So this, I can say it's periodic at every instant. So you don't have to factor in this, but you have two sinusoids here. The first sinusoid has got a period of 2 pi by 3, and the second sinusoid has a period of 2 pi by 4. So what about the combination of these two signals? What is the period of these two? So you have seen that the period of the linear combination of two sinusoids or two sinusoids can be written as two periodic signals can be written as the LCM of the periods of the individual components. So which is LCM of 2 pi by 3 and LCM of 2 pi by 3 and 2 pi by 4. What is the LCM of 2 pi by 3 and 2 pi by 4? That's equal to 2 pi. So therefore we can definitely see that the period of this periodic signal x tilde of t, I'll put a t0 here. So this is t0. The period of the periodic signal x tilde of t is therefore equal to 2 pi. What is there for omega naught? Ashwin, can you please unmute your mic and answer? Ashwin, is Ashwin present in today's class? Ondalla. Ashwin, please unmute your mic. Ajay, please see that Ashwin is in the class today.
Sir, network issue എന്തുകൊണ്ടെന്ന് ഇപ്പോൾ പറയണ്ടായിരുന്നു.
Ajay, can you answer this? What is the frequency, fundamental frequency omega naught? Fundamental frequency omega naught. This is the fundamental period T0. What is omega naught therefore? 2 pi by T0. This 2 pi by 2 pi. So therefore omega naught is equal to 1.
1.
So 1 radians per second. Omega naught is 1 radians per second. Okay, so CK you can write as Ck is equal to x of t, which is equal to, so what I'm going to do in order to find out the exponential Fourier series, I will just expand the cosine and the sinusoids and the sine term in terms of complex exponentials. So this becomes 4 plus 2 e raised to j 3t plus e raised to minus 3jt by 2 plus 3 into e raised to j 4t minus e raised to minus j 4t by 2j. So I will expand this. So if I expand this, this will be 4 plus 2 by 2. So that is just e raised to j 3t plus e raised to minus 3jt plus 3 by 2j into e raised to j 4t minus 3 by 2j into e raised to minus j 4t. Is that clear? So therefore, since the fundamental period omega naught is equal to 2 pi by t is equal to 1, and we can therefore we can write x tilde of t is equal to sigma over k ck e raised to jk omega naught t. So where c0 from the expression, what is c0? What is c0? C0 will be equal to 4. C0 is the constant. What is C1, C2? There are no terms for C1 and C2. What is C3? Because the fundamental frequency is 1, the fundamental frequency exponential would be e raised to jt, because omega naught is equal to 1. So e raised to j3t would be e raised to j3. If I just write e raised to j3t, so e raised to j3t is equal to e raised to j3 into k into omega naught t. And you know omega naught is equal to 1. So this term is equal to e raised to j3k t, which means k is equal to 1. K is equal to 3. This should be e raised to j3t is e raised to j k into t. Omega naught is equal to 1. So e raised to j k into 1 into t. So that is e raised to j k t. So k is equal to 3. So for this term k is equal to 3, and for this term k is equal to minus 3, and this is for k is equal to 4, and this is for k is equal to minus 4. So C0 is equal to 4, C3 is equal to 1, C minus 3 is also equal to 1, and C4 you get as 3 by 2j, and C minus 4 is also equal to minus 3 by 2j. C4 is equal to, this is 3 by 2j, and C minus 4 is equal to minus 3 by 2j. So is this understood? Okay. Is this understood? Do you need further clarification here? Namita?
Yes, sir.
Okay. ഇവിടെ ഒരു ചെറിയൊരു മിസ്റ്റേക്ക് ഞാൻ എഴുതിയിട്ടുണ്ടായിരുന്നു. C4 is equal to 3 by 2j. C minus 4 is equal to minus 3 by 2j. All other Ck are equal to 0. Now, you have one interesting property here. You have a cosine wave of frequency 3. You have a sine wave of frequency 4. But the combination of these two has got a frequency equal to 1 hertz. Is that understood? I have a cosine wave of frequency 3. I have a sine wave of frequency 4. But the combination of these two is giving you a periodic signal of frequency 1. So what I'm going to do here is, so I will just add one slide here, and I will plot the I'll just open a whiteboard session. And we will try to plot the line spectrum for the sequence. So the line spectrum gives you some interesting results. or I'll plot it here itself. So let us plot CK. So C0 is equal to 4. You don't have C1, you don't have C2, you have C3 is equal to what? 1, C minus 1 minus 2 are equal to 0, C3 is equal to 1. And then you have C4 is equal to minus 3 by 2j. So if I'm going to plot modulus of CK, this would be 3 by 2j. So 3 by 2j would be something like this. So 4, this is 3 by 2j, this is 4. 0, 1, 2, 3, 4. This is minus 1, minus 2, minus 3, and this would be minus 4. Right? So you see that you do not have a fundamental frequency component here because the value at plus or minus 1 is equal to 0. And you don't have a first harmonic at plus or minus 2. Instead, you have the second harmonic of amplitude 1 at 3 and minus 3, and you have the third harmonic of amplitude 3 by 2j. Here, the magnitude being equal to 3 by 2. So this is 3 by 2. This is also equal to 3 by 2. So even though there is no fundamental frequency component here, the composite signal has got a frequency equal to 1 hertz, 1 radians per second. Is that understood? That's a very interesting result. Because what we have is, okay, so what we have here is, even without the fundamental frequency component, you have a composite periodic signal that has got a frequency equal to 1 radians per second. You see that there is no 1 radian per second component in this vector. So it is not necessary to have a line at the fundamental frequency component. Is that understood? That's a very interesting result. So there is no need for a line to exist at the fundamental frequency component of the composite periodic signal. I hope that is understood. Now let us look at the Parseval's power theorem. We will prove the Parseval's power theorem as follows. We will evaluate the power in the time domain by evaluating 1 by t0 integral over t0 modulus of x of t whole square dt, which is equal to 1 by 2 pi integral minus 5 to plus 5 modulus of x of t whole square dt, which I can write as 1 by 2 pi integral minus 5 to plus 5 4 square dt plus minus 5 to plus 5 2 cos 3t whole square dt plus minus 5 to plus 5 3 sine 4t whole square dt. So see that cos 3t is 1 plus cos 6t by 2, and this is 1 minus sine 8t by 2j. 1 minus cos 2t by cos 8t by 2, 1 minus cos 8t by 2. So this you can expand as 1 by 2 into, so this evaluates to 32 pi, and this evaluates to, so you see that cos 60, you are looking at the total area under 6 cycles of a cosine wave from minus 5 to plus 5. So what is the total area under 6 cycles of a cosine wave? So total area would be equal to 0 because there is as many positive area, there is as much positive area as there is negative area under 6 cycles of a cosine wave. So I will draw a cosine wave here. I will draw a few cycles. So if you look at the cosine wave, if you find out the area under a cosine wave under an integer number of cycles, you see that there is as much positive area as there is negative. So therefore the total area under 6 cycles of a cosine wave, as also here under 8 cycles of a cosine wave, are also equal to 0. These two is equal to 0. So this evaluates to 1 by 2 pi into 4 plus this evaluates to 1 by 2 pi into 9. So 1 by 2 pi into 4 plus 1 by 2 pi 9. So this total value evaluates to 16 plus 2 plus 9. So 16 plus 2 plus 9 by 2. So which is equal to 45. by 2 watts. 45 by 2 watts. Now we will prove this in the frequency domain. You only need to square and add the lines in the magnitude spectrum. So P0 plus P3, that is power of the DC component plus power of the second harmonic plus power of the fourth harmonic can be written as 16 plus. This is 1. P3 is 1. So 1 square is 1. P minus 3 is 1. So that is also equal to 1. This is 3 by 2j. So modulus of that is 3 by 2. So 3 by 2, the whole square is 9 by 4. This also is 9 by 4. And this evaluates to therefore 45 by 2 watts. So thus we have proved the Parseval's theorem. I hope this is understood. Can someone give me feedback regarding this? Aparna?
Yes, sir.
Joel Abi? Joel?
Yes, sir.
Okay, I hope this is understood. So
Yes,
you can prove the Parseval's theorem by evaluating the power in the time domain and in the frequency domain. So the Parseval's theorem shows that the power you can compute in the time domain as 45 by 2 watts and the frequency domain as 45 by 2 watts. So I'll give you some homework. You do, there is no need to treat as an assignment, but I insist that you complete this homework. I think we will be doing something on similar lines today. So assignment 2 is to determine the exponential and trigonometric Fourier series of x tilde of t. So this is the first x tilde of t. You have a square wave 0 to t0 by 2, except that the square wave is not symmetric. So there is an easy way to look at this, which is to just subtract a by 2 from this a by 2 from this waveform that we have drawn here. And just subtract a by 2 from this waveform. I'll use a different color to plot the waveform here. Now, what is its amplitude, Joel? If I subtract a by 2 from this, what is the amplitude?
T by T0 by 2.
This amplitude is A.
Okay. A.
Okay. So, what is the amplitude here? What is the amplitude? I am subtracting a by 2 from this waveform. Amplitude amplitude be a by 2. A by 2, right? What is the negative amplitude?
Minus A by 2.
Minus a by 2. Now, you also have to tell me this is plus a by 2, this is minus a by 2. What will be the nature of this waveform? Is it an odd signal or an even signal? What do we have here? Is it an odd signal or an even signal? Odd signal even signal x of t is equal to x of minus t. Odd signal is when you have x of t is equal to minus x of minus t. So you can tell me whether this is an odd signal or an even signal. So for that you only need to look at whether this is an odd signal. Very good. So if it is an odd signal, what does that tell you about its Fourier series? If it is an odd signal, what does it tell you about the Fourier series?
See.
We have seen some properties of the Fourier series. So you have seen that if a signal x of t can be represented as x tilde of t can be represented as x e tilde of t plus x o tilde of t, then x e tilde of t can be has got a Fourier series given by ak, which is a real part of ck, and x o tilde of t will have a Fourier series given by bk, which is the even part, which is the imaginary part of ck. So this is something that we had proven. So understand that this is an odd signal. So it is enough to find out the Fourier series of the second waveform that we have drawn, and then you can add a by 2 to the periodic expansion for the sequence to get the sequence. Now, Vinayak, class Vinayak, please unmute your mic and answer. Okay, so Ajay, you can answer this. What do you expect the DC component of the second waveform? This second waveform, the DC component is there.
Sir, A by 2.
This is DC, രണ്ടാമത്തെ waveform, the DC component. ഇത് മുകളിലോട്ട് A by 2 ഉണ്ട്, താഴേക്ക് minus A by 2 ഉണ്ട്. അപ്പോൾ ഇതിന്റെ ആവറേജ് വാല്യൂ എത്രയായിരിക്കും? ഇതിന്റെ ആവറേജ് വാല്യൂ പോസിറ്റീവ് സിംഗും ഉണ്ട്, നെഗറ്റീവ് സിംഗും ഉണ്ട്. 0 ആയിരിക്കും. ഇതിന്റെ ആവറേജ് വാല്യൂ 0 ആയിരിക്കും, അല്ലേ? So which means
yes,
if you expand this, you will find that you will get the DC component C0 as equal to 0 for this. Now you can tell me this has been shifted upwards by A by 2. So for this, C0 would be equal to A by 2 because it has been shifted upwards, right? Clear അല്ലേ? കാരണം ഇതാണ് ഞാൻ ആദ്യം എക്സ്പാൻഡ് ചെയ്യുന്നത്. അതിൻ്റെ കൂടെ A by 2 കൂടെ ആഡ് ചെയ്ത് കഴിഞ്ഞാൽ എനിക്ക് ഈ സിഗ്നൽ കിട്ടും. Is that understood?
Yes, sir.
Okay. So what we will do is we will evaluate CK. Right? What we will do is we will evaluate CK directly from whatever you are given in the figure. We will not instead use this. അപ്പോൾ ഇത് നമുക്ക് അറിയാമെങ്കിൽ ഇതിലേക്ക് ഡയറക്റ്റ് പോകാമായിരുന്നു. This we can evaluate as from the figure 1 itself. We can write CK is equal to 1 by T0 integral over 0 to T0 by 2 A e raised to minus jk omega naught t, which you can write as A by minus jk omega naught T0 into e raised to minus j omega naught t between 0 to T0 by 2. കാര്യം എന്താണ്? ഇനി ഇതിനിടയ്ക്ക് ഇതിന്റെ വാല്യൂ 0 ആയതുകൊണ്ടാണ്. Okay, so this you can write as A by jk omega naught T0 omega naught T0. So you see that omega naught T0 എന്ന് പറഞ്ഞാൽ എന്താണ്? Omega 0 into T0. What is omega 0 into T0? Omega 0 is 2 pi by T0. So 2 pi by T0 into T0 will evaluate to 2 pi. So this is 1 minus e raised to minus jk pi. So e raised to minus jk pi we can write as minus 1 the whole raised to k. So this is A by jk 2 pi into 1 minus 1 the whole raised to k. So we will make some observations here. So you see that C0 is equal to A by 2 for the first waveform. C0 is equal to A by 2, which you can directly evaluate. C0 is equal to A by 2. C0 എന്ന് പറയുന്നത് ഇവിടെ omega 0 equal to k equal to 0 to കഴിഞ്ഞാൽ this would be a division by 0. So that instead of evaluating that, you can directly evaluate C0 by using the expression C0 is equal to 1 by T0 integral 0 to T0 by 2 A dt. So this is A dt. So this evaluates to A by 2, and you see that when k, if I put k as an even number, so whatever I discuss here is now important. If I put k as an even number, which means if I write k is equal to 2m, what would be the value of ck? That is, what would be the value of C2m? What would be the value of C2m? I'll ask this question to Alvin Benail.
Yes, sir.
Okay. So if I put k is equal to 2m, that is
Zero.
k is even. Oh, this evaluates to 0. So obviously it evaluates to 0. So if k is even, this evaluates to 0. If k is odd, that is C2m plus 1 evaluates to A by J into, instead of K, I write 2n plus 1 into pi, right? Into,
Yes, sir.
so this, because this is 2 now, so that 2 will get cancelled. So this is A by J into 2n plus 1 into pi. So which means I can write my Fourier series as equal to A by 2 plus A by J pi plus sigma m equal to minus infinity plus infinity 1 by 2m plus 1 e raised to j 2m plus 1 into omega naught t. Is that understood? This is understood, Alvin? Because
Yes, sir.
C2 is equal to 0. So I might as well replace m by k, so that is not going to make any difference. So except that you know that the even values are equal to 0. You know that the even values C2m are equal to 0. You only have lines in the odd frequency domain. So which means you will have a spectrum something like this. So you will have a C0 for this waveform. You will have a C0. Then you will have C1 and C minus 1. You might have C1, C minus 1. You will not have C0, C2 and C minus 2. Then you will have C3 and C minus 3. You will not have C4 and C minus 4 because there is no even component. So this should be the shape of your spectrum. Is this understood? Alvin?
Sir, മനസ്സിലായി.
Okay. So we'll move on now. Now this question you can work out by yourself. So I have a waveform which is now even. This is even. The previous one is odd. This is odd. This one. Rather, this one is odd. Now if I add a by 2 to this, it will become this component. So you see that you will have only odd harmonics here. Now this is even. So this I want you to work out by yourself. So I will not do this question in the class. Then you can use the time shifting property. Time shifting property. I've seen the time shifting property of Fourier series. So you can apply time shifting property to the result that we have obtained here, and then try to find out the Fourier series expansion for this. Can you do this? Alvin, do you want me to work this out in the class? I hope we can complete this now. Alvin?
Sir, try ചെയ്ത് നോക്കാം.
Try ചെയ്തിട്ട് നാളെ ഉത്തരം പറയണം. Now we will do this question in the class. Find and sketch the magnitude spectra for the following signal. So this is a rectangular wave. I will not call it as a square wave because it has got a duty cycle that is different from 50%. What is duty cycle, by the way? Alvin? What is duty cycle?
Sir, പീരീഡിന്റെ ലെങ്ത്.
ഡ്യൂട്ടി സൈക്കിൾ എന്നുള്ള വാക്ക് ആദ്യമായിട്ടാണ് നിങ്ങൾ കേൾക്കുന്നത്? Duty cycle is T on by T on plus T off. Duty cycle is defined for a square wave. So if this is equal to 1 by 2, then it indicates that T on is equal to T off. So that's you have a square wave. So if this is not 1 by 2, then you have what is known as a rectangular wave. Is it understood? So here we have deliberately marked the width of the pulse as is equal to D. D may or may not be equal to T by 2. So I'm not saying that D is equal to T by 2. So the on period might not be equal to the off period. So that is why we have used a general value D here. So 0D, T, etc. So this is a case where D is smaller. This is a case where D is even smaller. So here I will take D is equal to T by 4, and this is where D is equal to T by 8. Okay. So let us try to find out the magnitude spectrum for the signals here. So we will find out the magnitude spectrum for the general case for a width is equal to D. So ck you can write as 1 by t0 integral 0 to t0 x tilde of t e raised to minus jk omega naught t dt. So this you can write as 1 by t0 because it is existing only from 0 to d. You can write this as integral 0 to d a e raised to j minus jk omega naught t dt, which evaluates to a by t0. So I will write this as a by t0 into within limits e raised to minus jk omega naught t by minus jk omega naught t between 0 to d. I will write this as a by t0 into 1 by jk omega naught into 1 minus e raised to minus jk omega naught d. See how we progress now. What we will do is we will take e raised to minus jk omega naught d by 2 outside so that we can express the term inside in terms of a sine wave. So a by jk omega naught t0 into e raised to minus jk omega 0 d by 2 into e raised to jk omega 0 d by 2 minus e raised to minus jk omega 0 d by 2. So what I will do is I have a d by 2 here. To ensure that I have a d by 2, I will multiply the numerator and denominator by d by 2 and this will become a by 2 0. So again omega 0 t0 is equal to omega 0 t0 you can write as equal to 2 pi. So this becomes a by t0 into d into sine k omega 0 d by 2 by k omega 0 d by 2 into e raised to minus jk omega 0 d by 2. Now this is to get an expression like this. Whatever manipulations that we have done is to get an expression in this form. Sine k omega 0 d by 2, that is sine k omega 0 d by 2 divided by k omega 0 d by 2. Sine k omega 0 d by 2 by k omega 0 d by 2. What we will call this as? We will call this as SA of k omega 0 d by 2. We will call this as SA of k omega 0 d by 2 into e raised to minus jk omega 0 d by 2. E raised to minus jk omega 0 d by 2. So this SA we will define here now. SA of x is equal to sine x by x. SA of x is equal to sine x by x. We will call sine x by x as a sampling function. ഇതിന് വളരെ ഇമ്പോർട്ടൻ്റ് ആണ് ഈ സാമ്പിളിംഗ് ഫംഗ്ഷൻ എന്ന് പറയുന്നത്. അതിന്റെ റിലവൻസ് എന്താണെന്നുള്ളത് നമുക്ക് മനസ്സിലാവുന്നത് ദാറ്റ് ഈസ് വെൻ വി ഡിസ്കസ് ദി സാമ്പിളിംഗ് തിയറി. A sampling function is represented as sin x by x. It's also called as sine over argument. So you have a sine of x over the argument, sin x by x, sine over argument. So sampling function is also called as sine over argument. So SA of x you can read as either a sampling function or you can call it as a sine over argument. And a related function is sin x, which you can write as sine pi x by pi x. Sin x you can write as sine pi x by pi x. So what is sin x therefore? Sin x is SA of pi x, right? This is understood? Sin x is SA of pi x. So now we will look at some properties of this sampling function. കാരണം ഇത് അറിഞ്ഞാലും നമുക്ക് ഇതിനെ നേരത്തെ ഔട്ട്പുട്ടിനെ നല്ലൊരു കോമ്പാക്ട് ഫോമിൽ റെപ്രസെന്റ് ചെയ്യാൻ പറ്റും. So this is how the SA of x plot looks like. So SA of x is equal to sine x by x. So what is the value of sine x by x at x is equal to 0? Namita, can you tell me that? What is the value of sine x by x at x is equal to 0? നമ്മൾ നേരത്തെ കണ്ടിട്ടുണ്ട് ഈ ക്വസ്റ്റ്യൻ കേട്ടോ. ഞാനത് സാമ്പിളിംഗ് ഫംഗ്ഷൻ പറയാതാണ് പറഞ്ഞിരുന്നത്. നമിതയ്ക്ക് പറയാമോ? എങ്ങനെ കിട്ടി? എങ്ങനെ കിട്ടി 1 എന്നുള്ളത്? x is equal to 0. അപ്പോൾ 0 by 0 എങ്ങനെ ഇവാലുവേറ്റ് ചെയ്യും? When you have an expression that evaluates 0 by 0 or infinity by infinity.
Not defined.
Not defined.
Evaluate
something known as
L hospitals.
L hospitals rule. So what is
cos
L-Hospital's rule say? Then you
Derivative.
take the
Cos.
derivative of, so cos x by 1.
Mm.
So put x is equal to 0. So what is this equal to?
1.
1. So you have the value of sampling SA of x at x is equal to 0 is equal to 1. So this is an important result. SA of x is equal to 1 for x is equal to 0. And now what is the value for SA of x at x is equal to pi? So sin x by sin pi by pi, sin pi is 0. So at pi it becomes 0. Again at 2 pi it becomes 0. Again at 3 pi, likewise minus 5 pi, minus 5, minus 2 pi, minus 3 pi, etc. it becomes 0. So if you plot sampling of x, SA of x, you see that SA of x peaks at x is equal to 1, x is equal to 0, and it crosses 0 at x is equal to plus or minus m pi, plus or minus m pi. So at pi it's 0, minus 5 it's 0. At plus 2 pi it's 0, minus 2 pi it's 0. Plus 3 pi is 0, minus 3 pi it's 0. And you have a peak, you have the first peak at x is equal to 0, and you have the first negative peak at x is equal to what? This is 3 pi by 2. At x is equal to plus or minus 3 pi by 2, you have your first negative peak. Then you have x is equal to plus or minus 5 pi by 2. You have the next peak, which is positive. X is equal to plus or minus 7 pi by 2. You have the next negative peak and so on. Now, if you look at sinh x is sin pi x by pi x. Sin pi x by pi x. So sinh x allows you to represent the x-axis in terms of real numbers. So if I have x is equal to 0, this value is sin pi into 0 by 0. Sin 0 by 0, well, let's see 1. If I put x is equal to 1, then this becomes sin pi by pi. So sin pi by. So this is 1, this is 2, this is 3. So you have the peaks. You have the first peak at 0, the next peak at, which is a negative peak at 1.5 minus 1.5, the next positive peak at plus or minus 2.5 and so on. And you have 0 crossings at 0, you have 0 crossings at plus or minus 1, plus or minus 2, plus or minus 3, etc. So this is your sinh function. Okay. I hope this is okay. Is it understood? Can I move forward? So therefore the Fourier series of the waveform is Ck is equal to A into d by t0. നമ്മൾ നേരത്തെ എഴുതിയ expression നോക്കേണ്ടി വരും. A into d by t0, A into d by t0 into SA of k omega 0 d by 2 into e raised to minus jk omega 0 d by 2. So you have a sampling function which is multiplied by a constant given by a into d by t0. So the amplitude increases by a into d by t0. Now that total sampling function or total sine or argument function has to be multiplied by an additional phase shift of e raised to minus jk omega 0 d by 2. E raised to minus jk omega 0 d by 2. So let us look at the magnitude for d is equal to t0 by 4. So C4, Ck for d equal to t0 by 2. So I will write the magnitude of Ck. So Ck, this is the magnitude of Ck. So Ck, magnitude of Ck is a by 4 sin k pi by 4 by k pi by 4 modulus. So ഇതിന്റെ magnitude എടുക്കുമ്പോൾ ഇതെല്ലാം മുകളിലേക്ക് വരും. Which means if I take the magnitude, this will become like this. മനസ്സിലാകുന്നുണ്ടോ? If I take the magnitude, this negative also will go upwards. So a by 4 sin k pi by 4 by k pi by 4, where d is equal to t0 by 4. So d by t0 becomes 1 by 4. So this is sin omega 0 into d by 2 will become sin k pi by 4 by k pi by 2. This becomes a by 8, magnitude spectrum line becomes a by 8 sin k pi by 8 by k pi by 8. So that is plotted here. അതിൻ്റെ ഒരു ഷേപ്പ് കാണിക്കാൻ വേണ്ടിയിട്ടാണ് ഇങ്ങനെ വരച്ചിരിക്കുന്നത്. സോ ദിസ് ഇസ് ദി എൻവലപ്പ് ഓഫ് ദി lines in the line spectrum. Whereas for 1/8, you see that the envelope is something like this. Like the barking in a continue. So at some point it will go up, and some point again it will be like this. So this is modulus of CK versus K. This again is modulus of CK versus K. So I hope this is understood. Now we move on to another question, which is to find out the Fourier series of the impulse train delta T0T. Delta T0T you call as an impulse train. Impulse train, a train of impulses. So delta T0T is plotted here. You have impulses that are located T0 seconds apart. So mind you, we are looking at continuous time Fourier series. You are looking at continuous time signals. So therefore, these delta T's are Dirac deltas. So the Dirac delta real. Dirac delta is your area of the Dirac delta would be equal to 1, and it excessively at T equal to 0. So delta T0T can be written as sigma over K equal to minus infinity plus infinity delta T minus K T0. This is your Fourier series for delta T0T. So this can be expanded as a Fourier series sigma over K Ck e raised to jk omega 0 t, where omega 0 you can write as 2 pi by t0. So now Ck you can write as 1 by t0 integral minus t0 by 2 is somewhere here plus t0 by 2 somewhere here, integral over 1 period എന്നാണ് പറയുന്നിരിക്കുന്നത്. Integral minus t0 by 2 to plus t0 by 2. What is the function in one interval? Let me ask this question to Alvin. Alvin Benil.
Yes, sir.
What is this function in one interval? I am taking only one interval here. From here to here, this is one interval. ഇതിനകത്ത് ഒരു ഇമ്പൾസ് മാത്രമല്ലേ ഉള്ളൂ.
Yes, sir.
So delta T0 of t will become delta t in one interval. This is delta t into e raised to minus jk omega 0 t dt. So this you can write as equal to, because from the sampling property of the impulse functions which you have studied in the introductory sessions, this is sampling e raised to minus jk omega 0 t at t equal to 0. So this sample, if I put t equal to 0, this will become 1. So this is 1 by t0 and 1, and therefore equal to 1 by t0. So what does it mean? Ck is equal to 1 by t0 for all k, because there is no term containing a k here. This is a constant 1 by t0 throughout. മനസ്സിലായല്ലോ? C0 is equal to 1 by t0, C plus or minus is equal to 1 by t0, C plus or minus 2 is equal to 1 by t0, and so on. So delta T0 of t can be written as sigma k equal to minus infinity to plus infinity delta t minus k t0, which is equal to 1 by t0 sigma over k equal to minus infinity to plus infinity e raised to jk omega 0 t. So that is my Fourier series expansion for the impulse string. So let me plot the line spectrum now. So line spectrum, you see that the line spectrum is also consisting of impulses, right? ഈ ലൈനിന്റെ ഒക്കെ ഹൈറ്റ് ആണ് ഇത് ഇമ്പൾസ് ആണ്. ഇമ്പൾസ് എന്ന് പറയുന്നത് ഹിയർ ലെറ്റ് us think of a Kronecker delta. These are not Dirac deltas. Instead these are Kronecker deltas, because അതിന്റെ ഹൈറ്റ് 1 by t0 ആണ്. You know what is a Kronecker delta? Alvin, what is a Kronecker delta?
At 0, the value will be 1, and at all index.
Yes, at 0 the value is equal to 1, and at all other indices the value is equal to 0. So this is 1 by t0 and a Kronecker delta. So again you have a 1 by t0 and a Kronecker delta, 1 by t0 and a Kronecker delta, which are shifted. So this is the line spectrum. So you see that you have a impulse train in the time domain. You have as its Fourier series an impulse train in the frequency domain. This is a Fourier series, mind you. Later we will look at the Fourier transform of this. So this is a Fourier series. And the Fourier series consists of Kronecker deltas which are separated by omega 0, right? Because this is k omega 0. This is 0 into omega 0. This is 1 into omega 0. This is 2 into omega 0. Now, Alvin, you can also tell me what will happen if these two if lines in the impulse train in the time domain come closer to each other. If these are very close to each other, if the separation decreases, that is, if T0 is reduced, what will happen to the separation between the lines in the line spectrum? Parayama? Increases. Why? Because this is T0, this is omega 0. And T0 and omega 0 are inversely proportional. Because omega 0 is equal to 2 pi by T0. So when these lines become closer to each other, these become farther and farther apart. When these are farther and farther apart, these become closer to each other. Is it understood? Okay. So, ഇപ്പോൾ നമ്മൾ കണ്ട ഇമ്പൾസ് ട്രെയിനിന്റെ ട്രിഗണോമെട്രിക് Fourier series expansion കൂടെ ഇവിടെ എഴുതുന്നത്. So the trigonometric Fourier series you can write as Ck is equal to Ak, since you can write Ck is equal to Ak plus Abk. And you see that this function that you have here, the function that you have here is an even function. ശരിയല്ലേ? കാരണം നമ്മുടെ ഇമ്പൾസ് ട്രെയിൻ എന്ന് പറയുന്നത് ഒരു ഈവൻ ഫംഗ്ഷൻ ആണ്. This is your impulse train. This is an even function. So what about an even function? What do you have the result for an even function? You see that bk is equal to 0 for the even function. So if you can write Ck is equal to Ak plus Abk, you see that the function is even, so you can write Bk is equal to 0, and Ak you can evaluate as 2 by T0 integral over T0 x tilde of t cos k omega naught t dt. So cos k omega naught t dt, which evaluates to 2 by T0 because it's again sampling cos k omega naught t at t equal to 0. So this evaluates to 2 by T0. So the trigonometric Fourier series can be written as A0 by 2. Again, A0 by 2 would be equal to 1 by T0. So because 2 by T0 by 2 is 1 by T0 plus 2 by T0 into sigma over k equal to 1 to infinity cos k omega 0 t. So this is your trigonometric Fourier series expansion. And finally, this is the last question that we are going to attempt today. So I have not fully completed this because this will use a result that we have previously arrived at. Find the Fourier series of the waveform in figure 1 by using the differentiation property of the Fourier series. So that I have plotted here for these. Time differentiation. So if I have d by dt of x tilde of t, you see that d by dt of x tilde of t is having a Fourier series given by jk omega 0 into ck. So ck is multiplied by jk omega 0. So how will you get ck? So this we will do now. D by dt of x tilde of t has a Fourier series given by jk omega 0 ck. We will call this as ck dash. This will call as ck dash. So x tilde of t will have a Fourier series given by ck, which is equal to ck dash, that c dash k, sorry, I have to read this as ck dash divided by jk omega 0. Don't put dash as differentiation. You are not doing any differentiation here. I just want to use a different notation for the new Fourier series coefficient of the derivative of x tilde of t. This is not differentiation. So ck dash എന്നാണ് ഞാൻ ഇവിടെ എഴുതിയിരിക്കുന്നത്. So x tilde of t is equal to, x tilde of t has got a Fourier series given by ck, which is equal to c dash k by jk omega 0. ഇവിടെ ഒരു ചെറിയൊരു പ്രശ്നം എന്ന് പറയുന്നത് I cannot evaluate C0 from this. C0 കണ്ടുപിടിക്കണമെന്നുണ്ടെങ്കിൽ I have to divide this by 0. So C0 I cannot evaluate like this because there is a division by 0 involved. So C0 has to be found out from this expression directly. C0 ഇതിനകത്തുനിന്ന് ഡയറക്റ്റ് ആയിട്ട് കണ്ടുപിടിക്കേണ്ടി വരും. നമ്മൾ നേരത്തെ ഒരു ക്വസ്റ്റ്യൻ ചെയ്തിട്ടുണ്ട്. ആ ക്വസ്റ്റ്യൻ എന്ന് പറയുന്നത് ഞാൻ ഇവിടെ നിന്ന് കാണിക്കാം. You have done this previously, and before that we had evaluated the Fourier series of this. E square wave in the Fourier series നമ്മൾ evaluate ചെയ്തു. Okay, so we will need that result here. Or you can do that even directly. ഇതിന്റെ ഡെറിവേറ്റീവ് എടുക്കുകയാണെങ്കിൽ, if I take the derivative of this, let us see what is the derivative here. Now this is a straight line from 0 to t0 by 2 with a slope of a by t0 by 2, or slope is equal to 2a by t0. If I take the derivative of this, this is 2a by t0 from 0 to t0 by 2. And if I look at this range, that is from t0 by 2 to t0, from t0 by 2 to t0, this is a negative slope. So changes, what is the slope here? What's the slope here? Namita? ഈ ലൈനിന്റെ സ്ലോപ്പ് എത്രയാണ്? t0 by 2 to t0. നെഗറ്റീവ് സ്ലോപ്പ് അല്ല, ഇത് നെഗറ്റീവ് ആണ്. It moves from a to 0 in time t0 by 2. So that is a negative slope. Slope is minus 2a by t0. നെഗറ്റീവ് അല്ലേ? ഇവിടെ പോസിറ്റീവ് സ്ലോപ്പും ഇവിടെ നെഗറ്റീവ് സ്ലോപ്പാണ്. So this slope is minus 2a by t0. If I take the derivative of this, I will get the slope basically. So this is 2a by t0. This is minus 2a by t0. Now if I evaluate the Fourier series of this, then I can evaluate the Fourier series of this waveform by using your time differentiation property. How I can evaluate ck as equal to c dash k by jk omega 0, which is what we have seen. Right? Ck is equal to c dash k by jk omega 0. C0 you have to find separately. Now, ഈ പറഞ്ഞ ഇത് കാണുന്നുണ്ടെങ്കിൽ now you only need to look at this waveform 4a by t0 from 0 to t0 by 2 and 0 between t0 by 2 to t. You subtract 2a by t0, that will give you this waveform. Okay. Now I have not proved that here, so this is what you will end up with. I want you to work this out and find out what is the answer. Okay, so that is all about the questions on Fourier series. Now we will wind up today's class and I will start Fourier transforms in the next session. So I want you to go through all the workload examples in the textbook that I have uploaded on the Moodle page. Have you seen the textbook PDF copy that I uploaded on the Moodle page? Ajay, Kandirna?
Yes, sir.
Which was that textbook?
അയ്യോ സർ പേര് ഇരുന്നില്ല കണ്ടു.
അത് നോക്കണം. അതിനകത്തുള്ള വർക്ക്ഔട്ട് എക്സാമ്പിൾസ് എല്ലാം ചെയ്ത് നോക്കണം. We don't have too much time to look at all the different type of Fourier series problems. So basically what you need to do is you have to be familiar with your integration and differentiation skills. You have to see, verify, remember all the integration tables, and then you only need to apply the appropriate expressions for computing the Fourier series coefficients, and you also need to know the properties of Fourier series because that will help in solving many problems. Okay, we'll stop this for today and we'll continue today itself. Maybe today evening I will record a session and upload. Okay, thank you all.